Hello, thank you for watching my talk. I'm excited to be part of the program of the Haskell Symposium this year. I'm going to talk to you about functional reactive programming and specifically a useful interface to one of its most important features. These are techniques that arose repeatedly in my use of Yampa in game programming specifically. The main idea is that we're going to define a scripting language for FRP. What this language is going to do is going to simplify discrete switching. At the same time, it's going to maintain all of the continuous semantics. What we're going to end up with is an imperative style scripting interface that retains the notion of continuous time. I'm going to give you an outline of what we'll talk about. First, I'll go over signal functions and describe what I mean by continuous time and discrete switching. After that, I'll describe a monad for switching that will give us this foundation for this scripting interface. And then we'll talk about how to combine these discrete modes of signal functions in sequence in time. We'll talk about how to combine them concurrently. And then I'll go over some of the related and future work in this area. So a signal function is essentially a signal processor, and we treat them the same way an electrical engineer might treat signal processors in a circuit diagram. They have input and output signals, and these signals carry values that change over time, or they carry different values at different times. And the notation for these signal functions ends up looking very much like a block diagram for signal processing. The signals are polymorphic, so any type can be an input or an output signal. We compose signal functions out of other signal functions. So the output of one signal, or the output signal of one signal function can be the input to another. And we can combine signal functions in this way to produce more sophisticated behavior out of primitive ones. And I've shown here both a block diagram and the arrow notation that corresponds to it to demonstrate that we can write these things out. I'm going to show you mostly diagrams, but they can all be pretty readily converted into textual expressions. Switching is a different kind of composition from signal chaining, and it's one of the most important features of functional reactive programming with arrows. We can compose two separate compositions of signal functions together into one, where the combined signal function first behaves as the first composition and then at a later time behaves as the later composition. The input and output types stay the same, but importantly, we don't have to express everything in one single model, one single composition. We can have a composition that works well at one point in time, and then a composition that works well at a different point in time, and we can combine these into one processor that just switches between them. The interface to express this sort of switching can be somewhat limited. It's all right, but we're going to define a monadic interface to this switching that can replace or provide a nice alternative to the existing interface. And we'll see how it's more flexible and how it can be used. The existing interface is a combinator called switch, which takes, this is the simplest sort of operator. It takes an initial signal function that has an output signal that tells us when it's supposed to terminate. That gives us an event, a termination event. And then the operator also takes a continuation called k in this diagram. And the continuation takes the value produced by this termination signal and uses it to generate the next phase of the signal function that it switches to. So at the moment of termination, the value that is provided by the first signal function produces the next signal function. The continuation here defines the entire future of the signal function. So further switching is all defined as part of this continuation. there's almost an analogy between the types of the switch operator and the monetic bind operator. Both start with something that produces a value. That value is consumed by some kind of continuation, which then results in the whole thing having this final type. But the result of bind has this other wrapped value, the value mapped by the monad. But the switch does not. The result of switch does not produce this termination event. So we could define a slightly different operator that does do this and is thereby associative in the same way that the bind operator is. The crucial difference here is that the result of link, as we're calling, as opposed to switch, the result of link still produces a termination event, whereas the result of switch does not. And this is very easy. This is a very trivial change from switch given a continuation-based implementation like Yampa or Bear River. And as we'll see by the end of the talk, we can actually change the representation a little bit further to not use a pair of two outputs, but rather a sum type that can have either type of the normal output or the terminating output. And with that in hand, we can define a new abstraction. We can define a mode of a signal function as its own value, independent of any particular signal function. The representation of the mode is just going to be this signal function that has some input type A and then has this sum type as an output. And the bind operator is going to be basically equivalent to link modulo some unwrapping of the types. So what is this good for? What do we do with this? How do we define these modes and then combine them in sequences? Well, the first and most basic thing to do is to create a mode from a signal function. We can use a couple of different kinds of operators to turn a signal function into a mode. So the most basic of these is always. If we always behave as a certain signal function, we can produce a mode that never terminates, that never switches to something else. It always behaves as the signal function is given. We can also go a little further than that. We can impose a time limit on a signal function. So instead of creating a mode that always behaves as one signal function, we can create a mode that behaves as that signal function over a certain interval of time and then terminates. And we use this in a script, in our scripting language, as this example demonstrates. So we imagine we have a signal function for every frame of an animation that has been pre-rendered or pre-drawn. And the output signal of this signal function is of type image. So each signal function is producing a certain image constantly over time. And we use this over operator to turn each of these signal functions into a mode of the whole animation. So instead of always producing the first frame, say, we produce that over some interval, like 1/10 of a second. If we do this to all of the frames of the animation, we can get modes, monetic modes, that we can combine with the sequencing operator to produce what looks very much like an actor's script that says, do this task, do this activity, and when it's done, move on to the next one. When we have this in hand, we have this mode that can be represented by this sort of script, we can turn it back into a signal function for whatever application we have that uses signal functions, using an operator called run mode. And run mode just is essentially switch, taking the representative signal function out of the mode wrapper and applying switch and a continuation to it. Now, if we don't want to use a continuation, we can loop the mode back on itself and run the scripts over and over again by calling this operator loop mode, which is a simple definition based on run mode. We can use loop mode, for example, on our walk script to generate an infinite walking cycle animation that is represented by a signal function. So whereas each frame, the signal functions we started with, each frame produces an image constantly, and only one of them. This loop mode walk signal function will produce a changing image based on the script that we've given it in a loop that will look like a walking animation. So this is really convenient. We can do all sorts of animation scripts like this, and really we can script anything. This can be used for any signal function to script its behavior. Beyond going between signal functions and modes, we often want to go between modes themselves to transform one mode into another. And this is trivial with this representation. We can define this operator map mode, which maps a function to the representative signal function inside a mode just by applying the function to it. This is good for defining such things as a special termination condition, like an extra termination condition for a mode. We call that only until, and it takes an event source and adds it to the signal chain in this representative signal function. You can also define something called last out, which adds a recording of the signal function's output and produces it as the monadic value, as the mapped value upon the termination of that signal function. This is useful for transferring data, transferring state information from one mode to the next. We can see an example here of what only until is good for. We can take our previous infinite walking script that we make loop with forever, and we can then add a termination condition to it. So we might not know exactly when we want the walk to end, so we loop it with forever. But we take this external termination condition and apply it with only until. So in this case, center stage produces some event when the figure is at center stage or something. And only then does it move on from its walk animation to do sort of a pose for a certain amount of time and then start dancing, say. So this is great. We can take these scripts. We can take a script for walking that doesn't know anything about anything else and compose it with other animation scripts to produce larger animation scripts, and we can apply extra conditions to it, and we can extract state information from the output signal and pass it around and produce the next phase of the animation. This is already very useful. The paper defines some other modes that can be useful for this sort of programming. But I want to move on from composing modes in sequence to talk about how we can compose them in parallel. In something like Yampa or Bear River, the standard parallel switching operator is called p-switch, or p-switch b in this case. And as you can see from this diagram, it's relatively complex. The crucial thing to see here is that when the switching combination switches from one set of parallel signal functions to the next, it has this facility to freeze the state of those parallel signal functions and pass the states to the continuation that produces the next combination. Can this be any simpler? Do we have to use p-switch to get this state freezing facility? Well, one way we can get around that is by introducing it as sort of a new primitive operator on signal functions themselves, absent any parallelism. We can define an operator vein that turns a signal function into another one that has an extra output signal. And this extra output signal carries the original signal function's state as it evolves. So the signal that has this changing value carries the changing state of the signal function. And if we have that, then we can take two modes, apply vein to their representatives to get their continuously evolving state, and then capture that in an operator called mix. that will allow one to terminate and then the other to continue. So if we have this evolving state from both of them, when the first one finishes, the mix captures the state of the other one and passes it on to be the next phase of the combination. This is all applied within the representative signal function. So we can take two modes, extract the representatives, do this transformation to them, and then wrap it in a mode again. Now this requires a way of combining the outputs of them, and a way of combining the output of one with the sort of absent output of the other. So a good way to represent this is with a monoid constraint. And then when both of them are finished, the terminating values, the CD values here, are paired together and are the final return value, the terminating value of the whole combination. What this looks like in a script is, for example, something like a fireworks show. A sequence can contain mixed activities in line with unmixed activities, or sort of normal sequential activities. And like a fireworks show, we might have one sort of rocket that goes up, and when that's done, it will be followed by a combination of several rockets. And then when both of those are done, we can continue with the show. And this can go on and on. We can mix together activities that are themselves mixed together from other ones. And to continue that line of thought, we can extend mix with continuation passing to give us a nice interface to this sort of recursive mixing. We can define this operator voice, which uses mix and continuation passing to start a new thread, so to speak, of an activity that runs in parallel to the main thread of the script. And then we can use an operator called chorus, which takes those voices, like threads, and joins them into a single activity that waits for them all to finish. And in a script, this looks like something like this, where we might have a club where many people are dancing at once, and they enter the dance floor one by one, or maybe one at a time, and then two enter at the same time. And we can script these entrances with the main thread, but allow them to continue by using voice on them to start new threads for them. The paper gives more examples of combining modes and more examples of scripting, including automata for changing scenes, and we can also do GUI programming with this. We can get a natural form of GUI programming. That's all in the paper, but I want to save a little bit of time to talk about other work on this topic and leave some time for questions. In researching robot programs using FRP, several authors applied this idea of using a monadic interface to what they called tasks to script the top level behavior of a robot. So it might have a continuous mode of say moving around, but that can switch to a continuous mode of grasping, which can switch to a continuous mode of searching. This was prior to signal functions per se. An interpretation with signal functions of this task idea appears in the Yampa source code as early as 2003. Since then, there have been several examples of different interpretations of switching, notably as exception handling with monadic stream functions. And there's, in a recent paper about the FRP system called Rhine, there's a monadic interface proposed to this. In the future, there's room for more work on this. There could be a more concise interface to multi-threading. The continuation transformer, the CPS monad transformer that I used requires lifting the main thread modes, which is kind of verbose. There might be a better way of doing this. There might be a way of combining the multi-threading idea into the monad definition itself, the definition of modes itself. rather than requiring this external transformation. There's work on efficiency. I've not analyzed the efficiency implications of this in full. And I have pushed it with many threads for the multi-threading example. For instance, there may be some garbage collector pauses. So there's definitely work to do on investigating what optimizations might be possible. And then there's this this issue of delayed observation of switching that I said I'd refer to. We went from the switch operator, which uses this signal function whose output is this pair of a normal output signal and a termination signal, and replaced it with this either BC type. This prevents us from doing what Yampa does with delayed observation of switching in operators like dswitch or dpswitch. The advantage of using either BC is that it relieves us of having to worry about undefined outputs. So either there's a normal output value or there's a terminating value. We don't have to worry about what the output value is at the moment of termination, because it's always subsumed by the following mode. If we want to incorporate this feature of delayed observation, there needs to be some more consideration of what the representation is. That was a relatively quick overview. There's more detail in the paper, of course. Thank you for watching, and I look forward to discussing any questions you might have in the Q&A.